In this lesson, we are going to take the trigonometric functions that we've learned about and look at them through the lens of right triangles. So we've already defined our cosine and our sine and our tangent functions, for example, as ratios of either the y value to the radius of our circle, or the x value of a point to the radius of the circle, or the ratio of the y to the x value. But if you recall our picture that we drew along with us, it shouldn't surprise us that right triangles are involved, because that's exactly what gets formed in this picture. So if we just rename this x, y, and r, we'll have another way of looking at these trigonometric functions. So if I focus in on the angle theta here, then I'm going to name the y value my opposite side, because it's opposite of this angle. The x value here I'm going to rename as the adjacent side, adjacent meaning touching. And then of course the radius forms a side here that is also touching the angle, but the name I'm going to give this as the longer side, or the side that's opposite of the 90-degree angle, is the hypotenuse. So with this renaming, we have a different way of thinking of the sine function now. So instead of the y value of the point on the circle divided by the radius of the circle, I can think of this as the opposite over the hypotenuse. And my cosine I can think of as the adjacent over my hypotenuse. And then my tangent can now be the opposite over the adjacent. So the reason we're going to want to look at trigonometry in this way is because, especially in a lot of application problems, they set themselves up more naturally as problems that have triangles in them, as opposed to problems that have circles in them. And so it's important to look at these functions from the standpoint of a triangle. So here's kind of a cleaned up version of what we're looking at. So if I want to take the circle out of the picture, here's how we're going to define our sine, cosine, and tangent when we're thinking of right triangles as the context. So let's do an example where we put this into practice. Let's find the two missing sides of this triangle, and of course let's just make a note here. Anytime you see the little square in an angle here, you know that that means 90 degrees. All right, so let's take a look here. Let's find A first. Okay, so I'm looking at this angle of 41 degrees. It looks like I know the opposite of that angle, and I would like to know the adjacent. Okay, so based upon what I know and what I want to know, I can see that the tangent is really the appropriate trigonometric function to use in order to figure out what A is, because I know that the tangent of 41 degrees has to equal the opposite, which is 4 feet, over the adjacent, which is A. Right? Now, of course, I've got to get A all by itself, and if I currently have A in the denominator of a fraction, then I know that I can start solving for A by first of all getting it out of the denominator. So let's multiply by A on both sides. And so what I end up here is with, that's supposed to be a little time symbol there, A tangent of 41 degrees is equal to 4. And then of course tangent of 41 degrees, let's just remember that that is a number, right? You probably don't know that number off the top of your head, but it is a number nonetheless. So we can divide by it to get A by itself. Of course, we do that on both sides. And so what we get here is that A has to equal the ratio of 4 divided by the tangent of 41 degrees. Now this isn't exactly an application problem, but notice they do give us some context here. This is in feet. So I really don't want to leave my answer here as 4 divided by tangent of 41 degrees when we're talking about an actual length measure. So we're going to treat this like a story problem and know that we want to get an approximate answer in the end. And I know it's got to be approximate because 41 degrees is not one of those special angles where we've memorized our trig function values. So what I get there is if I round to the nearest tenth, I should get about 4.6 feet. And let's make sure that's reasonable. Well, if this is 4 feet here, this seems like it could very reasonably be 4.6 feet. Okay. Now, so now I know this is approximately 4.6 feet. But as I go to find the hypotenuse, I would like to avoid using this number here if possible, because of the fact that it is approximated. So really you shouldn't be plugging 4.6 anywhere if you can help it. And if you feel like you need to use the value A in order to find C, make sure you use the exact value here so we don't have a rounding on top of rounding. All right, so to find C, let's think about what it is that we want. Well, we want the hypotenuse. So I know I'm going to use either cosine or sine because they both involve the hypotenuse. But since the thing that I know is the opposite of 41 degrees, that means that the sine is definitely the one that I want. So we'll say the sine of 41 degrees is equal to 4 over c. And of course the algebra works the same way it did in the previous problem. We'll just multiply by c on both sides. So c times the sine of 41 degrees is equal to 4. And then I can divide both sides by the sine of 41 degrees because it is just a number. Looks like my fraction bar didn't, there we go, didn't get created. Sine of 41 degrees. So c is exactly equal to 4 over the sine of 41 degrees. But again, I'm going to get an approximation, and that gives me about 6.1 feet. That seems fairly reasonable, and I know that the hypotenuse is always the longest side, and so that certainly is true here. So let's do another example here, but notice this time the angle that they gave us was 60 degrees. And 60 degrees is one of those special angles where we're supposed to have memorized the sine values, the cosine values for 60 degrees without having to pull out a calculator or anything. And notice also up here it says to keep your answer exact, right? So that means that we're going to use our knowledge of the unit circle in order to determine what the exact answers are for x and y. All right, so let's begin here with y. So if I want to figure out y, I realize that's a hypotenuse. So that means I'm going to have to use one of the trig functions that involve hypotenuse, which would be sine or cosine. But because the thing I know is the adjacent, that means I would have to choose cosine because we know that the cosine of 60 degrees is the adjacent over the hypotenuse. Okay, so we have a very similar problem happening here to what we had in the previous example. So we've got our unknown in the denominator. So we'll multiply both sides by that unknown to get it to cancel over here. So y times the cosine of 60 degrees is equal to 15. And of course we know the cosine of 60 degrees is just a number. So we divide by it on both sides. And so that gives us our y value. So to get the cosine of 60 degrees, though, which we can do, we just need to recall that first quadrant on the unit circle, or use your left hand trick if you'd like, and that should remind you that the cosine of 60 degrees is 1/2. So this is 15 over 1/2, which of course we won't leave that way. This is 15 times the reciprocal 2 over 1. So that gives me 30. All right. So we know that the y value is exactly 30 here. Now, in the last problem, what we did was we used trigonometric functions to find both of our values. I think it's worth noting here, just as an aside, that at this point I could be done using trig functions because this is a right triangle. I know that 15 squared plus x squared is equal to 30 squared, right? A squared plus b squared equals c squared. So you could figure this out just from using the Pythagorean theorem. You could figure out what x is. And so if I subtracted 225 and subtracted 225, I would get x squared is equal to, so that would be 675. Now what's challenging about this is I would have to say, let's take the square root of 675, but this is not a simplified, definitely not a simplified way of writing this root. So remember, what you do is you look for perfect square roots inside of here, and clearly 25 goes into 675. All right, so that'd be 25 times 27. But then actually 27 has a perfect root in it as well, so this would be the square root of 25 times 9 times 3. So pulling out your 5, taking the square root of 25 and taking the square root of 9 and pulling out a 3, you end up with that, which ends up being 15 square roots of 3. Now, if that doesn't look very appealing to you, that's fine, because we can use trigonometry as well. So notice what we've got here. I'm looking for my x. I know, let's say my adjacent I know as well. So how about we use the tangent? So the tangent of 60 degrees is equal to x over 15. This time my unknown is not in the denominator of my fraction, so I can just attack this by getting x by itself by multiplying by 15 on both sides. So this means 15 tangent of 60 degrees is equal to x. And so my only task now is to find the tangent of 60 degrees. Well, the tangent of 60 degrees is the same as sine of 60 degrees divided by the cosine of 60 degrees. And we've already figured out the cosine, it's 1/2, right? And that immediately should ring a bell that on the unit circle, if my x value is 1/2, that happens when the y value is square root of 3 over 2. Feel free to use the left-hand trick for that. But that's just going to be 15 times square root of 3 over 2 times the reciprocal of the denominator 2 over 1 is equal to x. And then I can see those 2's canceling, and so of course I get 15 root 3, just like I did over here. In this example, we're going to take a look at a story problem that has a right triangle show up in it, and therefore allows us to use trigonometric functions to to solve this problem. So it says, from a 60-foot observation tower on the coast, a Coast Guard officer sights a boat in difficulty. The angle of depression of the boat is 3 degrees. How far is the boat from the shoreline? So what we have happening here is, I'm going to kind of draw this line of sight of the Coast Guard officer. So the idea here is, up here maybe is the top of the observation tower. And so this represents here the observation tower. They say it's 60 feet. And then way out here on the edge is our boat. And that's right there. All right, so when we talk about angle of depression, then what we mean is, if I'm the Coast Guard officer and I look straight out like this, just staring straight ahead out onto the horizon, out into the sky, then, excuse me for all that mess there, trying to use a straight edge. So if I look straight out and then all of a sudden I lower my gaze by just 3 degrees, right, then I'm going to see the boat. So here's 3 degrees right here. Okay. And so the question is, okay, how far is the boat from the shoreline? Okay. Well, I can see that I know the opposite side of this triangle, right? It's 60 feet, just like the tower is 60 feet. If the base of the tower is, right on the coast at sea level, then this side here is also 60 feet. And so if we want to know how far out the boat is, then we are looking for this side, x. So I can just look at what I've got here. I know the opposite. I want to know the adjacent. So this gives us that the tangent of 3 degrees is equal to 60 over x. All right, and the tangent of 3 degrees is not a special value, so we don't need to worry about getting the exact value at all. So we'll just multiply both sides by x to start with. So x times the tangent of 3 degrees is equal to 60. Then I can divide both sides by the tangent of 3 degrees, and I will fairly quickly have my answer. So when I approximate 60 divided by the tangent of 3 degrees, and of course I should mention in this example as well as the others that we want to always double check that we're in the proper mode. So if you get what seems like a really unreasonable answer, then check to make sure you're actually in degree mode when that's appropriate. So when I round that off, I get 1,144.9 feet. And if we kind of think through this scenario, clearly this adjacent side here is way, way larger than the opposite side. So this seems like a pretty reasonable answer.